The electrokinetic scanning probe, or shortly the ESP, is a non-contact device, operating on surfaces, in an immersed environment, at typical distances of tens of microns. The device consists of two open vertical channels, one for injection and the other for aspiration of liquids. By aspirating at a higher flow rate than the injection, the contact of the injected liquid with the surface is hydrodynamically confined to a teardrop-shaped footprint. The transport in the ESP is driven by a combination of electroosmotic flow, in which a uniform flow, proportional to the electric field applied across the channel, is generated due to the electric force exerted on the bulk liquid by the ions in the electric double layer. Electrokinetic migration of charged species in solution according to their electrophoretic mobility and gravity. The flow rates in each channel can be independently controlled using electrodes connected at the end of each channel, and an additional pair of ground electrodes on the surface. This video shows a bottom view of the ESP apex, injecting fluorescent beads along with a fluorescent dye through the left channel and aspirating them into the right channel. Owing to its low energy consumption, the ESP can be miniaturized into a self-contained compact device, which operates from a 5-volt input, and does not require any additional equipment. The ESP has versatile functionalities, including dynamic control of the footprint size, an ability to work with versatile processing solutions, local temperature control, analyte stacking at the reaction site, and rapid scanning and surface deposition. The size of the interaction site on the surface can be dynamically controlled by tuning the ratio between the electric fields applied across each channel. When the ratio is low, less liquid is aspirated, resulting in a larger confinement. As the ratio is increased, the size of the confinement decreases. Since electroosmotic flow is sensitive to the properties of the liquid in contact with the channel walls, such as ionic strength and pH, a confinement can be generated for any solution in the injection, by using a relatively low ionic strength immersion liquid. This leads to generation of a sufficiently high aspiration flow rate, and allows processing of surfaces using liquids at any pH, high ionic strength, and even organic solvents. An important condition to control for any chemical reaction is the temperature. Applying an AC electric field across the injection channel allows to heat the incoming solution through Joule heating, without affecting its flow rate. Visualization using a temperature-sensitive dye shows the heating effect is limited to the confinement. The temperature can be accurately controlled in the range between room temperature and 90 degrees Celsius. Analytes can be focused in the confinement area. In this mode, initially a regular confinement is established. However, over time, a significant increase of concentration is observed at the entrance to the aspiration channel. This focusing occurs when the electroosmotic mobility of the wall in contact with the injected solution is relatively low, and the electroosmotic mobility of the wall in contact with the aspirated immersion liquid is relatively high. If the electrophoretic mobility of the analyte is sufficiently high at the opposing direction, the analyte migrates backwards and exits the channel. Once in the confinement zone, the flow carries it back, leading to a highly concentrated zone. The system can be designed through a scaling analysis, by looking at the corresponding Peclet number in each zone. The scanning ability of the ESP allows to move from one location to another on the surface, with the confinement rapidly following the probe. This allows spatial deposition of any pattern on the surface. For example, patterning of DNA. In summary, the ESP is a non-contact probe, driven entirely by electric fields, able to combine dynamic control of the footprint size, compatibility with versatile processing solutions, and local control of the temperature and concentration at the reaction site, to create highly efficient surface reactions, using a compact and simple-to-operate device.